ZPF method of finding the voltage regulation of alternator. We know that in the case of alternator, the terminal voltage V, what we are getting from E, is changing because of three reasons. One is IRA drop. Then the second reason for change in the generated voltage to the terminal voltage is there is a IXL drop. The third one is the effect of armature reaction. In the case of a synchronous impedance method, that is synchronous reaction is treated as one more voltage drop equivalent to IAXA, where XA is added to XL, then it becomes XS. Means the armature reaction in the case of EMF method, is treated as one more the drop. However, in the case of MMF method, we know that once again there are three cause of change in the voltage. One is IRA drop, the second one is IXL drop, the third one is the armature reaction. In this case, the IXL drop is treated as one more armature reaction. In the case of EMF method, armature reaction is treated as a drop, whereas in the case of the MF method, the leakage reactance drop is treated as armature reaction. In the EMF method, armature reaction is treated as a one more voltage drop, whereas in the case of MF method, IXL drop is treated as one more armature reaction. Means these two are approximate method of finding out the voltage regulation, whereas in the case of ZPF method, what we are doing here is we are treating IRA drop as it is, as in the case of other two methods, and IXL drop is taken as IXL drop itself, whereas the armature reaction is treated as separately as an armature reaction only. Therefore, the ZPF method is most accurate compared to the EMF method and the MF method, because we are separating the armature reaction and leakage reactance drop. Whereas in the case of EMF method, the armature reaction is treated as a drop, whereas in the case of MM method, the leakage reactance drop is treated as the armature reaction. Okay. With this note, what is the procedure for finding out the voltage regulation using the ZPF method, that we will see now. Then the data required here for a Potier triangle method, because you are calling the ZPF method, or it is also called as a Potier triangle method, because the scientist who devised this particular method as a Potier, that is why it is called as a Potier triangle method also. To determine the voltage regulation using this Potier triangle method or a ZPF method, the data required are, once again, we need open circuit characteristics data, we need the short circuit characteristic data, as well as apart from that we have got zero power factor load characteristics. Means you have to connect the pure inductive load or pure capacitive load, and you have to load the alternator, and you have to draw the ZPF curve or zero power factor curve. These are the three data are required. One is OCC data, another one is short circuit data, the third one is ZPF power factor data. Using this data, you have to draw the graph of the ZPF graph, first OCC, ISC, short circuit characteristics, as well as the ZPF curve. But what I am doing here is along the y-axis I am taking the voltage. The base is once again the field current IF, or it is amperes. First, using open circuit characteristics, I will draw the open circuit characteristics. Then I also draw the ZPF curve using ZPF data. Okay, here for different value of the field current, what is the terminal voltage you are noting down in the case of ZPF characteristics. Whereas open circuit characteristics, you are aware of that is under no load condition. You go on changing the field current, you have to note down the generated voltage. Thereby you are drawing the open circuit characteristics. But in the ZPF characteristics, you have to connect across the alternator a pure inductive load or pure capacitive load. Then you go on loading the alternator. For different loading conditions, what is the field current and the corresponding the voltage you have to note down, so that you can draw the field current versus the terminal voltage. That what I am getting is ZPF characteristics. Okay. Once if you draw the characteristics, the steps involved in the case of the ZPF characteristics, just you have to remember here that only the 2 points are necessary to draw whole ZPF curve. That is, one point is what I am calling as the point P. The point P is the corresponding to the field current, which gives the rated terminal voltage, while the ZPF load is adjusted to draw the rated current. Means you have to load the alternator, you have to adjust the field current of the alternator in such a way that it has to deliver the rated current at the rated voltage. That is a point P. Means what is the field current required to deliver the rated current at a rated voltage that is corresponding to that particular field current and the rated voltage you have to note down with zero power factor load. That is a one point. The another point on the ZPF curve is the point P dash, which is corresponds to short circuit condition on the machine with the field current adjusted to give the rated armature current. Means it is nothing but your short circuit characteristics. That is, you have to note down the field current required to circulate the rated current under short circuit condition. That is a point P dash. P is the point corresponding to the field current which deliver the rated current at a rated speed. Whereas P dash is the field current required to circulate the rated current under short circuit condition. These are the 2 points you have to, if it is known these 2 points, then you can draw the whole ZPF curve. Then how exactly we are drawing that, I will explain with the help of this particular graph here. Just you have to take field current on the base axis, that is x axis, and along the y axis the voltage per phase you have to note down. First what I am doing is, first I am drawing open circuit characteristics. Then I will draw the airline. The airline means it is the line which is a tangent to the initial portion of the OCC, or it is the tangent to the unsaturated region of the OCC. That I am drawing air gap line. Then the point P I am putting here, P, it is corresponding to the rated voltage. At the same time it has to deliver the rated current. What is the corresponding? The field current it is required. Accordingly I am marked this P. That is, the P is marked corresponding to the rated voltage here, and at the same time it has to deliver the rated current. What is the field current? That you have to know. Therefore you have to mark this point P. The next point is a P dash. P dash, that is OP dash, is nothing but it is a field current required to circulate the rated current under short circuit condition. I know the point P, I know the P dash. Then the construction is very simple. You have to draw a vector from the point P so that it is equivalent to OP and it is start from P point. That is, just you have to look into. That is, I have to draw RP that is equal to OP dash. Then from the point R, you have to draw a line parallel to the airline. That touches at point N, S, then you can join SQ, or you can drop a perpendicular from S on this particular line, that is RP. Therefore, it is touching at the point Q on RP. Also, you can join RS. The procedure is simple. Draw RP is equal to Q OP dash, then draw line parallel to the airline, drop a perpendicular, join SP. Then from this triangle, SQ gives the IAXL drop. SQ gives IXL drop, whereas QP gives the field current required to overcome the armature reaction. That is, you convert this, or you measure this and you convert to the current scale, and you measure SQ with the scale and you convert to the voltage scale. So that what information I am getting from this PQRS, the PRS, this triangle is called as Potier triangle. In that, the QS, I told you, QS gives the leakage reactance drop, that is equal to IAXL, and that is same thing I marked here, IAXL. Then the QP, that is a QP, gives the armature reaction component, that is I am representing as IFAR, IF superscript AR, that is a QP, that is the current which is equivalent to the overcoming the armature reaction. Okay, that is IFAR I marked here. Okay, then this is how we have to find out the IFAR, that is armature reaction component, as well as IXL drop. Then to draw the whole ZPF curve, I told you there is only 2 points are necessary to draw the whole ZPF curve. Then what is the procedure for that? Then we know the Potier triangle. Go on putting the Potier triangle on OCC. Then this point P gives the point of the ZPF curve. You can look into that. That is same, this Potier triangle I placed at this particular point. Same thing, just you have to copy this and you have to bring on the one of the point on the OCC. Then this point is on ZPF curve. Similarly, one more Potier triangle I am placing here, means this point is also on ZPF, so that you can join that, then you are getting the ZPF characters. This is how you have to draw the ZPF characters. But that is what we need is from this Potier triangle is thus, that is SQ, we need QP, that you are already got it here. Then you have to proceed how to calculate the regulation using this Potier triangle. That is what I need is from this method is I want SQ and QP. That is how I represented here. I2AR or armature reaction is nothing but my IF2. It is also represented as IF2. Then we know the IXL, that is the drop, IXL drop. I know this is the corresponding to the rated voltage, rated current. Therefore, I can calculate what is the value of XL by IXL divided by IA. That what I am getting is XL. Then the steps inwards are very simple here. That is, we know that VB the terminal voltage on the full load. Then you have to add vectorially the voltage drop to the armature leakage reactance, also IRA drop. You have to the V, I have to add IXL as well as IRA if RA is given. Then the first step in the ZPF method is, first you have to get the EA. The EA is, that is internal voltage corresponding to the terminal voltage plus IRA drop plus IXL drop, but it is the vector sum. It is a vector sum. How I am calculating here is EA is equal to V an angle of 0 degree, because I am taking this as a reference. Then IA an angle of plus or minus phi. It is depending upon the power factor. Then RA plus JXL. XL I am getting from the Potier triangle. RA is given quantity. Rated current we know. At the same time terminal voltage also I know. Therefore you have to find out EA. Then what you have to do is, this is minus for lagging, plus for leading. The corresponding to EA you have to find out what is the IF1. That is corresponding to this EA, that is whatever the magnitude you are getting from this EA, this calculations, corresponding to that we have to find out the value of IF1. Then we know that the IF2 I am getting from the ZPF Potier triangle method, that is QP. Already I represented as IAR. IAR, that is the armature reaction component. This IF2 I know, IXL I know from the Potier triangle, IF2 I know from the Potier triangle. These are the two components I need. That is, using this I am getting the IF1. Directly from QP I am getting IF2, that is QP is nothing but this. There is QP, and from this IXL you are getting, then thereby you are getting XL. Okay. Next, we are finding out EA. Corresponding to EA we are finding out IF1, and from the QP I am getting IF2. Then once again, similar to your EMF method, you have to add IF1 and IF2 depending upon the power factor of the load using the formula, or you can factorial you have to add it. That is the total IF is equal to under square root IF1 square plus IF2 square plus 2IF plus or minus 2IF1 IF2 sin phi. Or it is cos 90 minus phi. It is one and the same. You have to find out either this you can as a cos 90 minus phi or sin phi directly. Here you can make use of. Then once we know the value of IF, then corresponding to this IF you have to project on the OCC, and corresponding value of E I have to find out. What you have to do, you are finding out the total IF. Once we know the total IF, that IF you have to project on the OCC, so that we will get the generated voltage E. Then once we know the value of E, then you have to find out the regulation as A minus V divided by V. This is how you have to find out the regulation of the alternator by ZPF method. Here in this particular method, we are separating both armature reaction as well as the leakage reactance drop. Therefore, this method yields the most accurate result compared to EMF and the MMF method.